Now, before we talk about the second fundamental theorem of calculus, let's kind of talk about what's going on when you're talking about the definite integral as a number versus the definite integral as a function of x. Now, if you just take the definite integral of a number and you've got numbers for both of your bounds, just constants, this is going to give you a number for your answer. If one of your bounds happens to be a variable, then what you're actually going to get is a variable or a function of that variable as your answer. So be careful with this because notice this is an integral with respect to t, and we're going to plug an x into it, which is going to create a function of x. So what this could look like, I've got capital F of x is the integral from 0 to x of negative sine of t dt, and I want to be able to find that for different values of x. So to do this, we would just calculate the integral as normal. So you could write this as the negative integral from 0 to x of sine of t dt. And we know that the integral of sine is negative cosine, so that's negative cosine of t, or cosine of t from 0 to x. So if you were to plug this in using the fundamental theorem of calculus, you'd get cosine of x minus cosine of 0. And we know that cosine of 0 is just 1. So this ends up being cosine of x minus 1. So if I want to evaluate this at three different values of x, f of 0 would be cosine of 0 minus 1, which is 1 minus 1 or 0. F of pi over 2 would be cosine of pi over 2 minus 1, which is 0 minus 1 or negative 1. F of pi would be cosine of pi minus 1, which is negative 1 minus 1 or negative 2. Okay, so basically this has given us a way to calculate this integral from 0 to any number x. Now, one way you can think about this is we're talking about the function negative sine of t. Okay, so remember the integral would calculate the area under the curve of that function. So the graph looks something like this, and I mean, obviously because this is negative, it's not really going to work. But if you were looking at a function that was positive, it would be like you were calculating a way to find the area from 0 to any x. Now, because this one's not positive on the whole integral or on the whole interval, it doesn't represent area anyway. But the idea is that you can kind of create an accumulation function of sorts, which will tell you you can plug in any value of x and find the definite integral up to that point. So this leads us to the actual statement of the second fundamental theorem of calculus. It says if f is continuous on an open interval I containing a, then for every x in the interval, the derivative with respect to x of the integral from a to x of f of t with respect to t is equal to f of x. Now keep in mind, this is a dummy variable right here, this t. So once you actually evaluate this, you're going to get some function in terms of x. Now think about this. This is going to end up being, some capital F at x, where capital F prime is equal to little f. And when you plug the a in, you're going to get a constant. So it makes sense if you were to turn around and take the derivative of all of that. All you would have left was f of x, no matter what number a is here, because it's just going to be a constant, and the derivative of a constant is 0. So in this case, when we're looking at it, the answer here is just the square root of 3x to the 5th plus 4. You don't have to do anything else, and because we're talking about a definite integral right here, there's no constant. So everything you took the derivative of is, all the constants are gone. So the second fundamental theorem of calculus just gives us the answer straight off the bat. Now, true, if you were trying to actually evaluate this thing, you would have to look at, okay, well, t can only have certain values because we're taking the square root of it and so on and so forth. But you do get that t equals 0 is fine because it's like a negative fifth root of, or a fifth root of negative 4/3 is like the smallest number that you can plug in there. So you can plug a 0 in and there's no issue there. It does have to be defined on this interval and continuous on it. So we're good in that case. But this would be the answer. Simple as that. Now, if you happen to have something a little more complicated, like for example this function, notice that what I plug in here is not just an x, it's an x cubed. So it's not going to be quite as straightforward as we would like it to be. if I were just to actually try and evaluate this, I would take the integral of cosine, which is sine of t, and I would evaluate that from pi over 2 to x cubed. So that would give me sine of x cubed minus sine of pi over 2. And we know that sine of pi over 2 from our unit circle is 1. And then if I were to turn around and take the derivative of this, I would have the derivative with respect to x of sine of x cubed minus 1, which using the chain rule would be 3x squared times cosine of x cubed, and then plus 0. So that would end up giving my answer. So notice that it's not just cosine of x cubed anymore. I can't just plug that in. I actually have to plug it, or I actually have to multiply it by the derivative of whatever that is. So in this case, basically what's happening by this, if you just wanted to work this by the second fundamental theorem of calculus, f prime of x would be cosine of x cubed times the derivative with respect to x of x cubed. So either way, you're going to get the same answer, but the basic idea is that if you have anything other than x up here, you have to actually multiply by the derivative of it. So you get the same thing either way. Now, one of the major applications of the fundamental theorem of calculus is what we call the net change theorem. This says that the definite integral of the rate of change of quantity f prime of x gives the total change or net change in that quantity on the interval from a to b. So the net change is going to be the integral from a to b of capital F prime of x with respect to x, which is capital F of b minus capital F of a. So for example, we have a problem that says a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where t is the time in minutes. So t is the time, and we know that t is between 0 and 60, so that means t is within that first hour. We want to find the amount of chemical that flows into the tank during the first 20 minutes. Okay, so we're going to let f of t be the amount of chemical flowing in t minutes. Okay. And we're told that the rate that it's flowing in, and remember, rate is a derivative, so f prime of t is 180 plus 3t. So we want the net change. We want to know the amount that's flowed in from t equals 0 to t equals 20. So the net change here is going to be the integral from 0 to 20 of f prime of t dt, or the integral from 0 to 20 of 180 plus 3t dt. And this is a pretty easy thing to integrate. This is going to be 180t plus, let's see, that'll be 3t squared over 2, which is going to be 0 to 20. From 0 to 20. So we'll have 180 times 20 plus 3 times 20 squared over 2 minus 180 times 0 plus 3 times 0 squared over 2. Be careful. Don't assume that you're always going to get a 0 whenever you plug that in. Sometimes you will, sometimes you won't. It just kind of depends on what the function is. But this will be 3600 plus 600 minus the 0 I get over here, or 4,200 liters of water. So in the first 20 minutes, 4,200 liters of water will have flowed into the tank. So you can calculate these types of problems using integration as well. And it's kind of an application of the second fundamental theorem of calculus. Okay, so that is 4.4. Before you move on to the next section, it might not hurt to go back and review the chain rule for derivatives. That would be in chapter 2, because we're going to use that pretty heavily. We're going to talk about kind of the version of that for integration.